Hi students. In this lecture, I am going to discuss electric dipole. See what is it? It is a system of two equal and opposite charges with a small separation between them. Let us see in detail. So take now two charges, magnitude same, but one is a positive, other one is negative, with a separation between them with a small separation. So take it as D. So this is what we call electric dipole. Q minus 2 with a small separation between them. So here we define one vector quantity that is electric dipole moment. A vector quantity is defined, that is electric dipole moment. Notation is P. It is equal to product of magnitude of one of the charges with the distance between them. Product of magnitude of one of the charges and distance between them. Q into D. And for this vector quantity, direction is direction is it is from negative charge to positive charge. Direction of dipole moment is from negative charge to positive charge. Let us see in our practical life examples of dipoles. If you take common salt, also known as a table salt, if you see chemical formula, common salt, that chemical formula is NaCl, right? Reading as sodium chloride, which is a combination of Na plus Cl minus, right? So having here two ions, positive ion and negative ion. So it's a charge plus one and its charge is minus one, right? And between these two now there is some separation. So this is now one dipole. This is one dipole, right? Suppose if you take water, its a chemical formula is H2O. So this is taken as H2O, H plus and H plus one more. Coming to oxygen, it is now minus 2, right? Charge plus 1, this is minus 2. So here you can take 1 minus 1 with this plus 1. This is one dipole. Remaining minus 1 and plus 1, this is one more dipole. It is now combination of two dipoles. Okay. That means water is having now dipole nature. Water is having dipole nature. Like this, we're having dipoles in our daily life. Let us now study when we place these dipoles in uniform electric field, right? Now see once, right? So definition part, system of two equal and opposite charges with a small separation between them. Electric dipole moment. This is now magnitude Q into D. Direction is from negative to positive charge. Okay, right. Now focus. If we place a dipole in a uniform electric field, let us study that. First, understand what is uniform electric field. Understand uniform electric field. Uniform electric field. See, its meaning is E bar is a constant. E bar is constant, or you can say E bar is the same everywhere. Okay. See what is meaning of that. E bar same means same modulus value, same direction at each and every point. Right? If E bar vector having same magnitude and same direction at each and every point, then that is called uniform electric field. Okay. Now we are placing a dipole. Let us now represent dipole. Suppose this is now electric field, that is E bar. Let us take let us take a dipole as showing with one vector. Suppose like this. This is now dipole vector. Okay, you can say dipole moment vector. Notation is here P bar. Okay. So this blue one is indicating dipole moment vector. Now that is making some angle with this electric field. Take angle is now theta. If you observe net force acting on dipole, see this is now negative charge and this is a positive charge. Direction is from negative charge to positive charge. Okay. Arrow indicates the direction part. And we have learned that force on a point charge is equal to Q into E bar, right? If charge is a positive, force will be along E bar. So if you take here, this is a positive charge. Field is now right side. So force also right side means like this. Okay. I'm taking a different color to make it clear. Direction of direction of force. It is now Q into E bar like this. And if you focus on negative charge, when charge is negative, direction of force will be opposite to E bar. So it is here opposite to E bar. Okay. So we are having here one is the right side, other one is left side. Both have same magnitude, right? Q into E and this also Q into E. So what is now net force on dipole? The first point is net force on dipole equal to 0. Okay. So first conclusion is when a dipole is placed, it is electric dipole in a uniform electric field, the net force on that dipole is 0 because directions are opposite, right? But if you observe, because of these two forces, the dipole rotates. Because of these two forces, the dipole rotates. Okay. That means now torque is acting on the dipole. What is it? Torque is acting on the dipole. And you can see this is a force. Both having same magnitude, directions opposite. This is what we call couple, right? So this we have discussed in rotation. Two forces of same magnitude, directions are opposite, they form a couple, right? Let us now calculate what is the torque produced because of these two forces. Okay, I will make a diagram clearly. Right. We want to calculate now. We want to calculate now what is the torque produced, right? What is the torque produced? This is electric field vector E bar Let us take now dipole moment vector. Dipole moment vector is now just to make it visible. I am drawing somewhat large. Let us take this dipole moment vector makes angle theta with the field vector. Okay. So now forces are sorry, this is Q into E bar, and this is also same, but direction is now it is left side. Okay. Then see what we can write. Torque equal to force is now Q into E multiplying with the perpendicular distance between them. What is it? The perpendicular distance between them. I will show here the distance how much? Perpendicular distance. That is now from that force to just drop a normal here. Now join like this. If distance is d between the charges, if distance is d between the charges, then this is separation. Let me call it as AB. Then AB length equal to d sine theta. It is now d sine theta. See here what we have written. Force multiplying force with perpendicular distance between the forces. This is now torque. Now this can be taken as in the place of Q into D, that is equal to dipole moment, that is P, remaining is E into sine theta. This is now modulus value. This is magnitude of torque. But if you want, what is the vector form? Then we can write tau bar equal to P bar, P bar cross C bar. Tau bar equal to P bar cross C bar. So you may get doubt here. Why only P bar cross C bar? Why not E bar cross P bar? Okay. Let us now cross check from diagram. So when force is applied, this is right side and this is left side. See, torque will be clockwise, right? Torque will be clockwise. Now this has to match with that one. If I am taking P bar like this and E bar like this, so take your right hand, place on P bar, curl fingers towards E bar. It is now clockwise, right? I am repeating. If you place your right hand on first vector P bar, curl fingers towards C bar. Now fingers are curled, it is a clockwise, right? How they're called? They are called clockwise. That means torque is now clockwise. So it is now matching with that, right? That's why it should be P bar cross C bar. Okay, right. And if you see from this one, we can say that torque is maximum. Torque is maximum if angle between P bar and E bar is 90. Okay, and torque will be zero if dipole is along the field vector. So if you are placing a dipole moment vector along the field, there is no torque. If angle is 90, torque will be maximum, right? Okay. This is regarding torque acting on a dipole, right? I hope you got it clarity. Let us now discuss potential energy of dipole. What is it? potential energy of the dipole. So let us erase this one and we can discuss now potential energy. Right. Right. Let us now discuss potential energy of dipole. Right. So heading is potential energy. Potential energy of dipole. Okay. Right. Let us now recollect. When you are taking a system, if it's a configuration changes, its a potential energy changes. Right. Then that change in potential energy is given by that change in potential energy is given by delta U equal to negative of work done by internal conservative forces. Okay. So this is what we have discussed first time in work energy power. Second time recently while discussing potential energy of 2 point charges. Right. There we got relation K Q1 Q2 by R in case of 2 point charges. Now once again same thing, it is delta U equal to negative of work done by internal conservative forces. So first we have to focus here what is a system. Okay. So we are placing now dipole in a uniform electric field. What is it? We are placing dipole in uniform electric field. Okay. Let us take this is now direction of electric field. Okay. Let us take now dipole. Let us take now dipole. Right. I have taken too much right here. Let me reduce the length. Oh, completely erased. Okay. No issues. Let me draw once again. It is now right. Suppose this is now dipole moment vector P bar. Okay. Right. See now, let us say at one instant, this vector making angle theta with an electric field vector. It is making theta. So first we are focusing here. What is the system? So we are taking dipole moment and electric field as system. It is dipole moment vector and electric field as a system. Then electric force acting on the dipole becomes internal force. Okay. And because of this electric field, now torque is acting on this. Okay. Let us now calculate work done by this electric field. Okay. That means we are going to calculate work done by the internal conservative forces, right? Then see what happens. So we are calculating here work done by electric force, that is equal to integral torque. It is actually writing here tau bar dot d theta bar. Okay. Then see what we get. It is tau bar dot d theta bar means tau into d theta into cos of the angle between those two vectors. I am repeating tau into what is our torque here? When angle is theta, torque will be it is a PE sin theta, that is a torque, that is torque. Because of this electric field, torque is now clockwise. If you see carefully, when dipole rotates clockwise, theta value decreases. Okay, that means torque is now clockwise. D theta, I am writing here modulus value. I am writing modulus value here. It is minus d theta. Okay, so why minus means theta 2 minus theta 1 is negative. Since it is now rotating clockwise, theta value decreasing. So final value minus initial value will be negative. Okay. So d theta itself is negative. So negative of negative positive. Okay. Therefore, angular displacement, it is a clockwise. Torque also clockwise. So between these two vectors, angle is now 0. Therefore, writing here, cos 0. Okay. See carefully. This is now modulus of torque. This is modulus of torque. This is modulus of d theta bar. This is modulus of d theta bar. Why negative means d theta itself is negative, negative of negative positive. And between these two vectors, torque is clockwise, d theta bar also clockwise. Since both are clockwise, between them angle is 0. So cos 0. Right? I hope you got clarity. Now go for next step. It is now I'm taking a PE outside integration of a sine theta minus d theta, or take minus outside integration of it is a PE sine theta d theta, integration of a sine theta d theta, it is minus cos theta, minus minus becomes a plus, remaining is now it is PE cos theta, and limits are from theta 1 to theta 2. Okay, that means now this becomes PE into cos theta 2 minus cos theta 1. Okay, right. Let us now continue here. So we got here work done by electric force, but delta U equal to negative of that work done, right? Negative of that work done. And what I can do here, or I can take here, it is minus delta U, right? Minus delta U. Writing here, U value when it is a theta 2 minus U value when it is theta 1. Okay. That is equal to negative of change in potential energy. Work done is equal to how much? Negative of change in potential energy. So I have taken that here. Now what we are doing is here, we are taking one assumption. We are taking one assumption, that is, so we take one assumption, that is, for this system, when theta equal to 90, potential energy is zero. We are taking one assumption, or you can say one reference point, we can say, when theta equal to 90. See, what is the meaning of this? If dipole moment vector makes angle 90 with electric field vector, then for that system, potential energy is zero. If you take this assumption, okay, let us take theta 1 is 90. Let us take theta 1 is 90. Theta 2 equal to theta. Okay, what I am taking? Let us take initially theta value how much? 90. Finally value how much? It is theta. So theta 190, theta 2 value, it is theta. Okay, right. Now substitute these values in this one. Let us, okay, in this one. Then see what we get. Theta 1, what we have taken here? Theta 1 is now 90. So this value becomes 0. Okay. The remaining is here minus, right? Minus is here left. Take this minus 2 right side. Remaining will be u of theta 2. U of theta. Because we have taken theta 2 as theta. I am taking minus 2 right side. Minus, minus, minus. What else left here? Pe. We have taken theta 2 as theta. Theta 1 is 90. So this value becomes now 0. So finally what is left? It is minus Pe cos theta. Okay. This is now potential energy, right? When it is angle is theta. The same thing can be taken in terms of vectors, that is minus P bar dot E bar. Now see carefully. Now see carefully. Between these two vectors, if angle is a 0, see what is meaning of that? If dipole moment vector is along field vector, if dipole moment vector is along field vector, then potential energy will be minimum, right? Get the point. That means if theta equal to 0, potential energy is minimum. Potential energy minimum. That is known as stable equilibrium position. If you take theta value 180, that means if P bar is opposite to E bar, then if theta equal to 180, then potential energy is maximum. That is what we call unstable equilibrium. What is it? Unstable equilibrium. Okay. I hope you got a clarity. Okay. Right. Now do one thing. Let us take one small problem here. A small problem, that is initially this dipole moment vector makes angle 0 with this E bar. How much? It is 0. Means it is now along E bar. Okay. Initially dipole moment vector makes angle 0 with E bar. Let us now rotate dipole to a small angle theta. How much angle? It is through a small angle theta. Okay. Then see what is a torque. Okay. I am writing here. What is the torque? So first we have taken, initially it was along E bar, equilibrium position, or you can say stable equilibrium position. Now rotating the dipole through a small angle theta, that is anti-clockwise. What is this? Anti-clockwise. Then torque is how much? Torque equal to, it is a PE sine theta. Since theta is very small, in the place of a sine theta, writing as theta. Okay. Yeah. And if you observe carefully, we are rotating anti-clockwise, but torque is clockwise. I am repeating, we are rotating anti-clockwise, but torque is clockwise. So take here negative sign. Okay. Now this net torque equal to I into alpha. From this we are going to get alpha equal to minus PE by I into theta, right? So it is of the form alpha equal to minus omega square into theta. Minus omega square into theta. That means now this dipole is executing simple harmonic motion. I am repeating, this dipole is executing angular simple harmonic motion. Okay. Then time period will be, then time period will be t equal to 2 pi by omega. That is 2 pi root I by PE, right? 2 pi by omega means this is now time period for small oscillations of a dipole. What is it? Time period for small oscillations of dipole. Okay. So we can expect problems basing on this result, time period. Okay. Right. I hope you got clarity. See once for these notes. Right. Uniform field force 0. Torque is a P bar cross C bar. Potential energy minus P bar dot E bar. Angle 0 stable. 180 unstable. Right. If theta is small, torque is, therefore time period is 2 pi root I by P. Okay. Right.